So on the one hand, we had we were given kind of a probability measure, an ensemble of B's, and so from this we kind of considered the solution of a drift diffusion equation, but let me start by the ensemble of B's. So we assume that this is kind of a stationary and centered Gaussian, and as such it's given by its correlation function, so which really is a correlation tensor because B is a vector field, is a drift field. So it's defined by the tensor product of B with itself, and because it's stationary it just depends on x minus y. So it makes sense to take the Fourier transform, and you get something which only depends on the wave number. And kind of last time I kind of described it more or less in words. Now let me write down the formula. So this is the Piclet number squared, so parameter epsilon squared. And then we had to introduce a small scale cutoff. So that means we take away all the large wave numbers by putting here the characteristic function of the set where the wave number is less than 1. And then I have to put a symbol, a Fourier symbol here, which kind of encodes the fact that B should be divergence-free. So that's essentially the identity, but I'd rather have to write it down as a symmetric form, EI tensor EI minus K tensor K divided by K square. And since I want to be precise, and K is a cotangent vector, and this should be kind of, those should be tangent vectors, I have to put the transpose here, but that's a detail. So this is the ensemble of B's. And then from this we got we were looking at the at U, which so B is kind of a function of B of x, and then we were looking at U, which is a function of xt, which is the solution of dtu minus script L of U is equal to 0 with initial data given by the identity. And this generator L is the Laplacian plus B gradient of U. So that's the generator of the drift diffusion process, so drift in this drift field B. And the interpretation of this function U is the expected position of a particle which at time t equal to 0 started at x at time t. So in some sense it's some averaged or the expectation of the Lagrangian particle positions. So that was one side, and on the other side we had kind of a Brownian motion B equal B tau on the space of 2 by 2 matrices of trace 0. And as I will explain today, it's kind of made unique by insisting that B is SO2 invariant, that B is such that Ito is equal to Stratonovich. I will explain what that means in a second or a bit later. And then there was a normalization, which was that E, if you look at the Frobenius norm squared of B tau, so that's a matrix, so that's a number, that this is equal to tau. So as I will explain, that uniquely determines this Brownian motion. And then from this Brownian motion, we defined a process f tau star tau with values in the matrices of determinant 1 via saying that if you fix the first parameter tau star and you let this parameter tau run, then this is given by a stochastic differential equation in the Stratonovich sense, driven by this Brownian motion on SL2. So this is for tau larger than tau star. And for tau less than tau star, f of tau star, tau is just the identity. So in a certain sense, you look at the SDE, which goes with this driver here. You start with the identity, but you don't start at the identity, which is kind of the natural kind of initial data on this group, because that's the neutral element of this group. But you don't start at the identity at time tau equal to 0, but at a variable starting time tau star. And before that, you set f to be equal to the identity. So f is equal to the identity for a while, and then at time tau star, it starts satisfying this differential equation. This time is not random. I mean, you could also make it random, but in the application, it will not be random. Yeah, that now comes in the formulation. So the theorem was connecting these two objects, which seemingly don't have much of a connection. So the theorem states that there exists a coupling, and I will make it explicit later on, between these two first objects, so between little b, the random drift, and capital B, the driver of this diffusion on SL2, such that for all time horizons t and for all points x, we have the following. We compare u of x comma t minus u of 0 comma t. So that's an increment of the coordinates at time t. And we compare it to this matrix valued process. I have to take the transpose here, the dagger, applied to x. And I fill this in a second. We look at the square. We divide by x squared. And I think I should create more space here for all time horizons and for all positions x. We take the time average over the time horizon, and then we take the expectation. So that's the expectation both with respect to the environmental noise in the drift B and the coupled driving force thermal noise in this Brownian motion. Then this is up to some universal constant less than epsilon squared times the expectation of f squared. And now I have to fill in these times. So there are two times where I need the definition tau of s is equal to the logarithm, the square root of 1 plus epsilon over 2, the logarithm of 1 plus s. So that's a quantity, that's a function tau which grows only very slowly in s, doubly logarithmically. There is a logarithm here, and there is a logarithm there. And in addition, there is an epsilon, which we think of being small. And what I need to put here is, as the potentially later time, the tau which corresponds to t, and at the potentially earlier time, the tau which corresponds to the length of the increment of the distance between 0 and x squared, comma, and here I need to put 0 tau t squared. So in this application, those are not random times, right? Those are, in a certain sense, this is a time which is related to the length scale in the problem, which is the distance between the point x and the origin. Of course, the origin doesn't play a special role here, but without loss of generality, I can take one to be the origin. and the other time is, the time which is connected to time horizon. And now if the origin is so if we are in the situation, so you should think of two cases. If x squared is larger than t, then this time, since tau obviously is monotone, then this time is larger than that. Then you're in the identity case. So then in a certain sense, this statement really looks like a kind of a Taylor expansion, and is telling you that u on these scales looks like the identity. So this is kind of the non-interesting case. But the more interesting case is the opposite regime, when x squared is less than t, and in fact when x squared is much less than t, so that this is still seen by tau despite the two logarithms. And then you're in this setting here where you actually see this stochastic, where you see this diffusion on SL2. Right? So that's the statement. So let me comment a bit on this statement. So at first it really looks like a kind of a Taylor expansion, because we're looking at the increments and we're subtracting a linear term. But that's a bit misleading, because this thing here depends on t. So there's an x dependence which is sitting here, which is benign, but there is an x dependence which is sitting here, which is not benign, which gives it a certain structure. So let me kind of make this slightly more precise. So, for instance, in particular, since tau is a function which, in a certain sense, very mildly depends on s, so you have to change s by orders of magnitude in order to see a variation in tau due to the two logarithms. And last time I tried to motivate why you see these two logarithms. So there was a kind of a heuristic argument. Last time I gave you kind of a somewhat very bold heuristic argument why you should expect this result. But it was really bold in the sense that it was based on saying, well, in this drift diffusion equation, at first we neglect the diffusion, and then we neglect, in a certain sense, the drift, in the sense that we can replace this operator by an effective diffusion. So it was, somewhat shaky, but it gave us exactly this expression here. And the main result, the main rigorous result is that this very bold heuristics, which I gave last time, in fact, is correct to, if you want, leading order in epsilon. But so this, coming back to what I just said before, this S dependence on tau is kind of weak in the sense that S has to change by really orders of magnitude so that you see kind of an effect in tau. So let me say, since tau only logarithmically depends on S, we obtain by taking the average over a ball of size of radius L in X, we would obtain the result, the expectation, or we do obtain the result, the expectation of the average in X and the average in T of 1 over x squared u of xt minus u of x0 minus f dagger tau of L squared, tau of t, x is controlled as above, as left side. No, here I mean 0.
No, the increment of u.
The increment, yes, I'm exactly the opposite, 0 and t. Thank you. So, so now in this form, what that's kind of a consequence of this result, if you're not asking for something that's pointwise in x, but averaged in x over a ball, then in a certain sense the scale over which you're averaging gets frozen in here, and that really now tells you that so on average, the function BL in x goes to u x comma t is close to an affine function. But this affine function depends on L. So the picture I would have in mind is that here you have x, here you have u. And if you're, let's say, on a very large scale L, if you zoom out to that scale, you will see one affine function. But if you go to much closer scale little l, you will see another affine function, right? So, so this is a little bit reminiscent of kind of what you would expect, you know, I mean, analysts would think of a BMO behavior. And in fact, this, in a certain sense, kind of confirms a conjecture in a recent paper posted by Armstrong, Bourabe, and Kuzi, who look kind of at the same drift diffusion process and make a statement not in terms of a parabolic equation as we do here, but in terms of an equation solved on a finite domain with Dirichlet boundary conditions. That this is a behavior which you should expect, that the slope depends on the scale you're looking at. And now in a certain sense, this kind of makes this very specific, at least in case of this parabolic equation, that the slope which you see, this affine function, this matrix which you see, in fact is given by this diffusion on SL2. So it's kind of makes that more specific. So perhaps that's kind of a good point to make a couple of, to refer to a couple of work. So this drift diffusion process, which I didn't even write down this time around, but which I wrote down last time, which was this process has kind of quite some history in this critical situation, and I mean, physicists kind of already looked at this in the 70s and the 80s, and but most of the previous work focused on one quite specific question, namely, look at this process and take a kind of a coordinate direction and look at the second moments of this process and understand how much this deviates from diffusive behavior, which would be that this quantity scales like t. That would be the diffusive behavior. And the physicists conjectured that indeed this should not behave diffusively, but slightly super-diffusively because of kind of the fact that one is in a slightly in a critical situation. And the first mathematical results in that direction were by Balintot and Benedict Valco in 12. And they indeed showed that this quantity grows larger than t by a double logarithm. So they indeed gave a first rigorous result that this process grows, kind of behaves in a slightly super-diffusive way. And then Canizaro, Hauenschmidt, Siebitz, which is the second part of his name, and Toninelli 10 years later, in fact, showed that this process behaves like predicted by the physicists, which is t times the square root of something, of a logarithm of t up to modulo double logarithm. And then in the same year, so Peter, Georgiana, myself, and Lihan Wang showed that one can get rid of the double logarithms. And then this year, Armstrong, Bourabe, and Kuzi showed that, in fact, it also holds in a quenched sense. You don't need to take annealed expectations. And what's interesting is kind of the techniques are very different. Well, I mean, quite different, although by now I think we also see similarities. These techniques from the probability community, in a certain sense, we're analyzing the generator as kind of as a on Fock space, and they were doing kind of a infinite dimensional or high dimensional Fock space analysis. Whereas our work and the recent work are using kind of, let's say, and I will get to this, more, let's say, standard homogenization techniques. So definitely correctors and so on. So so that is something not today, but perhaps I will address tomorrow, next time, or the last course. So there are, of course, more references to give here, and you'll find them in the paper, in the draft, which in the post which I said initially, and certainly many more references are in this paper. There are interesting connections to a variety of fields. So, okay, so let me now continue to draw a little bit of some more kind of consequences of this result, and then move on to what I called intermittency. And so for this I need a bit more space. So let's see how much space I need for the next result. So the next result is, in a certain sense, identifying or making a statement on the modulus of continuity of this field, which is almost Lipschitz by logarithm, which in a certain sense is already kind of suggested by this picture. So let me make this more precise. So perhaps this is now fixed. Perhaps I get rid of this here. So I write this formula here. Tau of S is defined as logarithm square root 1 plus epsilon square over 2 logarithm 1 plus S. And here, so from something which I will explain later, and which I already indicated earlier, that in principle we have a pretty good understanding of this diffusion on SL2, in the sense, at least in the sense, we get a very explicit answer if we look at the second, at the square of the Frobenius norm of these endomorphisms or matrices. Put a factor 1/2 here for convenient normalization. This is given by the exponential of t minus t star. And in fact, I should, since I'm also allowing the reverse order, I should write it's the maximum of this and 1. So you get this behavior trivially when you're in this setting, using that the Frobenius norm of the identity is equal to 2, or the squared Frobenius norm is equal to 2. And this more interesting behavior comes from this. So from this, we get the corollary. Let me call it 1 to be on the safe side. So provided we're on the regime where not only epsilon is small, but epsilon is small compared to the size of x in this specific way, then we find that if always looking at the same time average of 1 over x squared u of xt minus u of 0t squared. So that's now looking just at the increment of u and normalizing it, taking the square and normalizing it by x squared, taking the time average and then the expectation. Then this asymptotically behaves like the maximum of lambda of t divided by lambda of x squared and 1, where lambda of s is exactly what's after the first logarithm. 1 plus epsilon over 2 logarithm 1 plus s. So that's perhaps not so difficult to see that the relation between the theorem and the corollary. So it's using, think for a moment as if this right-hand side were equal to 0, then we could replace the increment by this matrix applied to x, and we can appeal to this characterization of the expectation of the squared Frobenius norm to get e to the power tau divided by e to the power tau star. Then you plug in what tau is and what tau is and what tau star is. You use the relationship between tau and lambda, and you find that this would be equal to that or that. And but of course, this is only true if kind of the noise to signal ratio is good. So you need this to be large compared to that. And that's exactly where now this condition comes from. So the corollary is really just a corollary of the theorem. Now let's look at this one again a bit more closely. So there is a way of kind of massaging it so that it becomes a bit more intuitive. So in particular, consider the function v, which now is a function which only depends on space, which you get from integrating in time a kind of an exponentially discounted function u. So why do I do this? Because this function solves a nice equation. That's kind of standard. It solves the resolvent equation of the generator with a very nice right-hand side. So it's our generator. It's the resolvent, which belongs to the generator. It's kind of the nicest right-hand side which you could imagine. But this theorem tells you, or this corollary tells you, that if you look at the increments of this function and you look at the L2 norm with respect of these, with respect to probability, then up to a prefactor which depends on t, which essentially is hidden here, this behaves like x over the 4th power of a logarithm of x in the regime where x is less than square root of t and where log x is much larger than 1 over epsilon squared, so very large x, but not too large x, 1 over epsilon 6. So the lower bound here comes from the fact that I want this term to be dominant over that term. And the upper bound comes from the fact that I need to satisfy this condition here. But as epsilon is small, this is a widening range of length scales which move out in an exponential way. And in this widening range of length scales, we see a modulus of continuity which is not quite Lipschitz, right? It's a little bit sub-Lipschitz by logarithm and by a very precise power of a logarithm, namely the 4th root of a logarithm. So this, again, is not super surprising. So the fact that you see something like this is not super surprising for the following reason, for, in a certain sense, purely deterministic reason. Because let's look at the equation. So let's spell out the equation. So there is this massive term which is kind of benign. There is the Laplacian, and there is the transport term which I'm going to write on the other side. And then there is this very benign right-hand side. And I should call it V instead of U. So what do we know about what do we know about the regularity of the right-hand side? So assume for a moment that V was as nice as you wish, so that the regularity of this term is really limited by the regularity of B. And by our assumption, B has wide noise scaling. On scales which are larger than 1, on wave numbers which are small to 1, so on scales which are large compared to 1. So white noise behavior means that if you translate it on a Hölder scale, you find that the exponent is minus dimension over 2. Here dimension is just the space dimension. And since we're in 2 dimensions, it's minus 1. So, and let me be more precise on an annealed Hölder scale, because if I would go to quenched Hölder scale, I would lose a little bit. Okay, so let's say in kind of in the best of all worlds, this right-hand side is in C minus 1, and therefore Schauder theory would suggest that the annealed Hölder regularity or Hölder scale of V should be 2 minus 1, which is 1. So a naive application of Schauder theory would tell us it should be Lipschitz. But of course we know, I mean PD people know that Schauder theory does not apply in the integer cases, right? So if we had worked with a slightly different noise, which would be slightly more regular or slightly more irregular, that argument would have made sense. But here there is it doesn't work, and it doesn't have to do with what's typically called the Kolmogorov criterion, that you lose a little bit like an iterated logarithm when you pass from an annealed to the quenched scale. So that's more a remark for people who know SPDEs, but it really is not surprising because of this deterministic fact that Schauder theory does not work in integer scale. But of course, so that should tell you that it's not surprising that you get that you get a logarithmic behavior, it doesn't tell you why you should get this power 1/4. That's not an argument why you should get this. In fact, if you think about deterministic theory, it's rather logarithm to the power 1 because of the fundamental solution. Okay, so that's one corollary. And now that's the right place now to explain intermittency. So let me move on and kind of compare this result to a result where we put a different exponent here. And then we'll see that things change in an intermittent way, in a somewhat anomalous or unexpected way. So let me write down this result. And that's perhaps the next section. So that's intermittency. And the idea will be that in a certain sense, and that's what I want to do today, intermittency on the level of f is perhaps not that surprising, and we can lift it from f to u. And let me write down what the result we get. So that would be so that would be the result on level of u. Let's call it proposition. So again, exactly in the same regime. Now I'm essentially copying what's on the right-hand side in this regime, and for any exponent, finite exponent p, so we're looking at exactly the same quantity, but now we take the pth expectation of this, and this is lower bounded by the right expression, I mean the expression which is there to the right in the previous result, not to the power p, which would be kind of the normal behavior, but to the power 1 plus 3/2 p minus 1. And it's the fact that 3/2 is strictly larger than 1, which is what I would like to interpret as an intermittent behavior, because it tells you that the modulus of continuity, not the polynomial part, which is always Lipschitz, like over here, but that the logarithmic part of the modulus of continuity depends on p. So the modulus of continuity depends on the norm in which, on the type of moments, on the degree of moments by which you, after taking the ensemble average, by which you measure your increments. So that is, in a certain sense, analogous to what people, what has been postulated or written down for fluid dynamics, for the Navier-Stokes equation, where people look at also increments of the Navier-Stokes equation, where there is, at least when you take a non-coercive expression, actually an exact formula for the third moments. But then when you look at other moments, you get a behavior which is, in a certain sense, anomalous or deviating from what one would naively expect, in a way which is slightly reminiscent of this one.
I'm a little confused
Yeah.
by the direction of this, but because x squared is downstairs, maybe I shouldn't be confused, right?
So this is a large number.
More, it bends this way. Okay, so it's not superlinear, it's sublinear.
It's so
So, many powers of x.
so this is right. So, but I mean, the way to think about it is probably just by looking at these two expressions. This is a kind of, in the interesting regime, this is a large number. And the pth moments are in an anomalous way larger than you would expect if moments were comparable.
Right.
Because this power here is strictly larger than p as soon as p is larger than 1. And in a very quantified way with this exponent 3/2, which hopefully I will be able to explain. And so that's what we'd like to, well, that's what we call intermittency. Okay, so.
Is there a connection? Did anybody look at Lagrangian intermittency? Because this is like Lagrangian, right? So it is. Did anybody compare, or are there any conclusions about how that should scale in Lagrangian intermittency? Because I'm familiar with the Eulerian pictures of increments of structure functions.
Yeah.
Not the consequences in Lagrangian.
So.
Did anybody look at that?
So I'm not aware of this. Now with this analogy, in a certain sense, here in this setting, I would rather call u the Lagrangian coordinates of the process, right? Whereas this type of phenomenon in case of Navier-Stokes is observed on the level of Euler, of the Euler velocity.
Right.
And now you're.
I'm asking whether or not there is an inference that can be made from intermittency at the level of the velocities described. So in other words, there will be sub-Hölder, there will be actually the bending of the Hölder exponent is really very severe. It's not linear like here, but this is linear in log. What you're
Yeah. So it's just on the log level.
Yeah. So there are proponents of certain behaviors of the structure function.
Yeah.
The structure functions tell you something on average about the nature of the velocity, which is not evidently not Lipschitz on the scales of interest. And then if you're going to try to infer something about correlations in the Lagrangian path,
Yeah.
I have no idea what those, if anybody did or if there are any.
Yeah, I don't.
So and how would that relate to behavior of diffusion? So the only things that I know are these old Richardson things, super-diffusive behavior of particles released.
Yeah.
So, but I don't know quantitative and connections.
Yeah.
There must be.
You know better about this.
I don't.
So.
I don't know. The Lagrangian, I know experimentally there is a Bodenschatz who started doing some experiments. It's really, and I think that there was no theory.
I mean, I know from, now I forgot the name, the French fluid dynamicist who was looking at the Lagrangian coordinates and said that on the level of the Lagrangian trajectories, you see the irreversibility most pronounced, that there would be kind of sudden decrease of velocities if you go to particle trajectories. So people have thought about this, about these, and the name will come back to me. He's somebody which Bodenschatz knows well. And okay, but here I think the analogy is that we're starting from a now it's erased from a linear drift diffusion equation, right? There is no nonlinearity. There's no the Eulerian equation, so to say, is not. And we put in a completely benign Gaussian statistics of the drift B, and what we get out is kind of this non-Gaussian intermittent behavior on the level of the Lagrangian coordinates. So, and my impression is that that might be, there might be more to it, but it's just that in this example, thanks to its criticality, we can compute a lot. And in kind of in a more general setting, I don't know how much of this can be actually computed.
No, it is definitely very useful that you're close to this So I think that one of the things that the reason why they probably shouldn't have good theories for the Lagrangian behavior in the hydrodynamic turbulence is that you are far from the truth, really very far. So far that particles might really want to do strange clumping.
Okay. Okay. Sometimes we're speculating that this type of intermittency might, because this function u in terms of the original stochastic process, so the one which I was motivating the problem with. This stochastic process, this function tells you how the expected particle position kind of gets ripped apart as a function of the initial starting point. And since this is a diffusion, the original process, the best way to think about it is, drift-diffusion equation in a Hamiltonian, in level sets, which are given by the Gaussian free field. So it's an interesting loop soup in which this particle diffuses, and it's super diffusive because as it diffuses, it finds these larger and larger loops, which the Gaussian free field has as level sets. And then, of course, you can imagine that, at some point, even if the particle distance is not so large, you will find a kind of a relative position where they're attracted to different loops. And then they will be ripped apart quite a bit. And I would believe that this intermittent behavior is I would hope that this intermittent behavior is a consequence of this feature of the dynamics. But that we don't know how to capture. Okay. Okay, so now my plan was, so in a certain sense now I've stated the main results, which I would like to kind of explain a bit. The ideas in the proof of which I would like to explain a bit better. And now the next step is to go to this this drift diffusion process on SL2, and tell you a bit about how we fix it in a canonical way, and in principle this was thought a bit as a little exercise, with juggling around with Ito and Stratonovich, or starting with Stratonovich and then going to Ito, and then telling you how kind of this type of intermittent behavior is very clearly seen on the level of the f, and because the f somehow is related to stochastic exponential, which is the key stochastic model for an intermittent, non-uniformly integrable behavior. So that's the plan, but I was more ambitious than I have the time, but I will start anyway, even if I have to continue next time. Okay, so perhaps I'm going to erase this side here. So that's 2, Ito versus Stratonovich. So anything here, and the definition of B. So recall that I first kind of defined the F process in terms of the Stratonovich formulation with the driver B, which is this kind of canonical Brownian motion on SL2, which I still want to define or explain. And so this is always kind of the sign for Stratonovich. And the best way to think about Stratonovich is that it's characterized and sometimes that's called Wong-Sakai theorem. It's characterized by smooth approximation. So meaning that if you have a sequence of kind of random paths which is smooth and which converge to our Brownian motion locally uniformly and almost surely, and you're solving this equation dfn fn dbn classically, then you're guaranteed that, provided you take the right initial conditions, that fn converges to f in the same topology. So the best way to think about Stratonovich is to think about this is what you would get if you use, you mollify your noise, you mollify your Brownian motion so that it's the infinity, you solve the classical ODE, and then as you let the mollification parameter go to 0, your solution will converge to the solution of Stratonovich. One consequence of this is that the chain rule holds. Which means that if you have an observable and you monitor your process along the observable and you want to see what kind of equation this one satisfies, you can just use the usual and let me write it down with a general sigma here. Then you can just infer it by applying the chain rule. And a consequence of this is that indeed what we wrote down, or what I wrote down before, satisfies a process on SL2 and not just on matrices. So application to our FDB and the observable, which is given by the determinant of the matrix. From this we learn that if B is in the Lie algebra, then F is indeed in the Lie group. So if the trace is 0, the determinant is equal to 1, or stays 1, stays constant. So therefore it was very natural to write this down in Stratonovich. But now if you want to think about the time discretization, mollifying is one way of approximating, of getting approximate solutions, but perhaps kind of a more practical way of getting approximate solutions is time discretization. But then Stratonovich is not very convenient because you need second order. More precisely, you need the midpoint rule.
Yes, midpoint is I was thinking about a little exercise to prove that midpoint discretization implies convergence of modifiers. It's a good exercise in probability.
Okay. Okay, so thanks for providing, at least for the YouTube participants, an exercise. So
I learned it with midpoint discretization. I think
so that means, it's not just enough to do an Euler discretization, which would be this one here if, the superscript denotes the time step, but you have to correct. And if you want to make the midpoint rule explicit, the correction which you get is sigma paired with the gradient of sigma at fk times this times bk plus 1 minus bk. So that's the right discretization which gives you Stratonovich. And then, of course, you look at this and you say, okay, that's complicated. Why can't I use a much simpler discretization, namely Euler? And I have to give it a different name because it is not just something different, but because it's well known that it would converge to something different. But as a discretization, it's very nice because it has one structural property which is extremely convenient, which is kind of, to use big words, is something like a martingale property. But I'm just copying this line here. Namely, since Brownian motion has independent increments, the previous fk tilde and the increment of the Brownian motion are statistically independent, and therefore the expectation of this term vanishes, which means the expectation doesn't change as you evolve. And that's kind of, in fact, it defines a martingale, which is now kind of a bit more than this, but essentially that. And but it converges to a different problem. This one converges to what's called Ito. So df tilde is equal to sigma b tilde, sigma f tilde, and here I don't put anything, and that's supposed to indicate Ito. So that's the difference between Ito and Stratonovich. And now if you insist of bringing Stratonovich into Ito form, well, then that can be done. You just have to compensate. If you compare the two time discretizations, you have to compensate for this term. And that's the famous Ito-Stratonovich correction. So, bring Stratonovich into Ito form requires, in our case, to write down df is equal to sigma df dB. That would not be the same thing, but if you correct it by 1/2, that's exactly the same 1/2 which is over there, the pairing of sigma with gradient of sigma, so that's just the directional derivative of sigma in direction of itself, at f paired with the what's called the quadratic variation of B, then these two objects, f defined here and f defined on the diagonally opposed blackboard, are the same. And that's the Ito-Stratonovich correction. And now this quadratic variation of B, because B is a Brownian motion, has independent increments, is in fact nothing else than the covariance of B at time 1. And you can convince yourself that this here is a canonical pairing between two bilinear forms. So there's no inner product involved here, and of course there shouldn't by proper invariance. And there is another thing one now may learn from this. So if we apply this to our sigma being the identity, so at f dB, either in Ito or Stratonovich, we get that this correction term vanishes. So Ito is equal to Stratonovich if and only if this correction term vanishes, which can be expressed in terms of the covariance of B, and it can be expressed as a certain contraction of the covariance, which consists in taking the matrix multiplication of these two matrix valued processes, and that expression has to vanish. So this is the matrix or endomorphism product. At first, if you look at this, it looks like you're asking for too much. A square will vanish, but that's not the case because this is not the full covariance. The full covariance is a 4 tensor, and here you're kind of requiring that a certain contraction of a two, which yields a two tensor vanishes. And okay, I think I have to stop. So what I'm going to do next time is I'm going to collect kind of another property, which is the normalization, and then I will appeal to a little bit elementary representation theory to say that these requirements indeed fix the Brownian motion on SL2. So there is a canonical Brownian motion on the Lie algebra, which gives a canonical diffusion on the Lie group, and that's the one which came up in all the arguments. And then I will tell you why this canonical object, and that's the only place where so far we need two dimensions, why this canonical object has intermittency, why it can, in fact, it can be compared to what's called a stochastic exponential, the simple inequality. And from this comparison, you can read off, you see that on the level of this object, the mean and the median are extremely different, which is kind of a sign of intermittency. And that's at the origin of the proposition which I raised. So that's what I will do next time. And then I will start with, in a certain sense, giving you the main technical tool, which is the homogenization result, which is behind connecting these two objects. Sorry for being a bit over time. Questions?
Yeah, no, because on the algebra here, why is the diffusion non-degenerate? There should be obvious reason why this condition doesn't allow for degeneracy.
Okay. I mean, so I can write down the diffusion in a very explicit way. So sometimes perhaps I'm trying to be too coordinate free. So the diffusion in the end will be kind of a combination of three Brownian motions multiplied by three matrices. So it's E1,
so we
D.
have three parameters, right? We're on
Yes. And in fact, so these matrices E1 and E2 are kind of a canonical basis of the trace-free matrices, symmetric trace-free. And E3 is the only basis of the trace-free antisymmetric, so rotation by 90 degree. And that would be kind of a naive way of writing down a Brownian motion on SL2, because this is a basis of SL2. These three matrices span the three-dimensional space of.
you wrote the same one.
And now you need to adjust these two parameters in a very specific way. And in particular, in order to have this property, this parameter has to be twice than this. And for the normalization, you want them to have a certain value. And then I think in the end, you need 1/8 here and 1/4 here, if I'm not mistaken.
At some point it's diagonal. In some form,
Yes,
this is diagonal.
yes. And then you also see that it's non-degenerate.
Well,
But
once it's diagonal in the basis, it's not.
yes. But in a certain sense, I find it easier to see it on this basis-free basis-free level.
Okay.
After a while, I find it easier. Okay.
All right, very good.
Welcome. Okay, so next is next week, right?